All right, we've now taken our first exam and we'll move on to chapter 4 with our introduction to probability. Before we continue on, we will need to introduce basic techniques and terminology that will allow us to calculate probabilities. Some of you may have already seen some of these topics before from our Math 110 finite mathematics class. A probability experiment, or what we call a trial, is any process with a result determined by chance. Some examples include flipping a coin, tossing a pair of dice, or drawing a raffle ticket. Each individual result that is possible for a probability experiment is what we call an outcome. The set of all possible outcomes is called the sample space. If we look at the following example, where we roll a single die, then the possible outcomes consist of we can roll a 1, we can roll a 2, roll a 3, roll a 4, roll a 5, or we can roll a 6. We can use this to write the sample space as the set 1, 2, 3, 4, 5, 6, where 1 represents rolling a 1, 2 represents rolling a 2, and so forth. Whenever we create a sample space, we put all of the outcomes in these braces, and that's how we denote a set. So outcomes are individual results of probability experiments, but when we put them together in a sample space, we create what we call a set. Again, when we write a set, we traditionally list out each member of the set using our braces. An event is a subset of outcomes from the sample space. So examples include if we flip a coin, but we focus only on flipping tails. Or if we roll a die, but we only focus on rolling an even number. Okay, so we restrict our probability, what we're looking at for our probability experiment. This is what we call an event. Let's look at an example. Consider the experiment in which 2 dice are rolled together. Use a tree diagram to help list the outcomes in the sample space. Now, a tree diagram is very useful when an experiment consists of several stages. This allows the outcomes to be organized in a systematic manner. The tree begins with the possible outcomes for the first stage and then branches for each additional possibility. To identify a specific outcome, list the sequence of events that describe a path from the top of the tree to the bottom of the tree. So in this case, we want to focus on 2 dice being rolled. So the tree begins with the 6 possibilities. So our first roll, so we're going to create an arbitrary point where we start. And now we look at our first event. Our first event is rolling the first die. So I can get a 1, a 2, a 3, a 4, a 5, or a 6. And now I look at my second roll. Well, from each of these first rolls, I can again obtain a 1, 2, 3, 4, 5, or 6. So I can roll a 1, and then I can roll a 1 again. I can roll a 1, and then I can roll a 2, or I could roll a 4, and then I could roll a 3, right? So this helps us organize in a systematic manner all of the outcomes for a larger sample space. So to find the sample space, we travel down each path, and we get the following result. We can roll a 1 and a 1, a 1 and a 2, a 1 and a 3, so forth. We can roll a 2 and a 1, a 2 and a 2, a 2 and a 3, so forth, and all the way until we end our tree and roll a 6 and a 6. So we have 36 possible outcomes for this probability experiment. A convenient way we could write this on paper as a set is by thinking of each outcome as an ordered pair of numbers. For example, both dice showing a 1 could be written as the ordered pair 1, 1. This could represent we roll a 1 and then we roll a 1. So both dice are showing a 1. Doing this for each entry, we get the sample space, 1, 1, 1, 2, 1, 3, so forth. So instead of drawing a picture, we can represent it notationally in a very similar manner. Let's look at another example. So consider the experiment in which 2 dice are rolled together. List the outcomes in the event the sum of the numbers rolled on the 2 dice equals 6. Okay, so now we want to look at something else. So it's very similar to what we just did. We're still rolling 2 dice, but now we want to restrict it. So we're looking at an event, and we're now looking at sums. So notice, if we start summing the 2 dice, we can view this in a different manner. So when we look at all of those possible outcomes, the ones that satisfy our sum equaling 6 are 1 and 5, 2 and 4, 3 and 3, 4 and 2, and 5 and 1. And there are no others. So again, check for yourself. For example, 5 and 5 wouldn't work because that sum is 10, which is not 6. Okay? So here's our possibilities for the event the sum of the 2 dice equals 6. There are 3 types of probability that we will discuss in this class. Subjective probability. This is just an educated guess regarding the chance that an event will occur. Experimental probability, or what you've probably seen if you've taken our Math 110 class, empirical probability. And this uses the outcomes obtained by repeatedly performing an experiment to calculate the probability. And finally, classical probability, or what you may have heard of as theoretical probability. And this is the most precise type of probability and can only be calculated when all possible outcomes in the sample space are known and equally likely to occur. Let's look at a couple examples. Determine whether each probability is subjective, experimental, or classical. So an economist predicts a 20% chance that technology stocks will decrease in value over the next year based on his knowledge of how other stocks have performed over the course of his career. So now, yes, this economist is probably very well educated, but it's still his prediction. So this is subjective probability because it's what he thinks will happen, okay? Let's look at another example. A police officer wishes to know the probability that a driver chosen at random will be driving under the influence of alcohol on a Friday night. At a roadblock, he records the number of drivers stopped and the number of drivers driving with a blood alcohol level over the legal limit. He determines that the probability is 3%. Notice in this case, he's repeatedly performing an experiment, and he's calculating the probability off of that repeated calculation here. So because not all drivers were evaluated, just the drivers at this roadblock, the probability is experimental. Remember that for classical, we need all of the population. So we only have the ones stopped at this particular roadblock. We don't have all of the drivers. And then finally, the probability of selecting a letter at random from the English alphabet is 1/26. And this is our classical probability because yes, all 26 outcomes are known and equally likely to occur. So this is an example of classical probability. And this is the probability that we will most commonly use in this class. Classical probability, with an exception to some problems we'll use our experimental probability. For our class, we will not focus on subjective probability, right? Okay, so, excuse me. In experimental probability, if E is an event, then we denote the probability that E occurs using this notation, the probability of E. So the parentheses are read of. So the probability of E is our F over N. So notice that this is just our relative frequency. If we go back to 2.1, remember when we were creating our frequency distributions, F over N was our relative frequency, right? So our experimental probability is really just our relative frequency. Let's look at an example. Suppose a fisherman wants to know the probability that a fish he catches in his favorite fishing hole is a catfish. For his experiment, he records the numbers and types of fish he catches 1 week. Suppose that during this week he catches 92 fish, 43 of which are catfish. Calculate the experimental probability of catching a catfish. So again, we take our frequency, so we want the probability of catching a catfish. So how many times did we catch a catfish? We caught a catfish 43 times. And over the total number of our fish caught. This is our sample size, right? This is our F over N. And we've caught a total of 92 fish, so our probability is approximately 47%, or 0.4674. And again, the book will tell you how to round appropriately. Traditionally, a lot of times for probabilities, we use 4 decimals. The probability that we will focus on the most in this class is classical probability. Sorry, this is a typo. In classical probability, this should say classical, if all outcomes are equally likely to occur, then the probability is given by this following. Now we have this N of E and N of S. So note that N of something counts the number of elements. So really we're just doing a count. Probability is just counting. So the probability that E occurs is the number of outcomes in the event E divided by the total number of outcomes in our sample space. That's what these letters represent. So let's look at another example. A sudden inexplicable drought causes all of the water from the pond to evaporate, leaving the fish in the pond exposed and vulnerable. Wildlife management is able to step in and save the fish, relocating them to other ponds nearby. During this relocation process, the exact count of all fish in the pond, along with their species, is recorded. There are 1,235 fish in the pond, and 541 of which are catfish. With this new information, what is the classical probability of the fisherman catching a catfish, assuming that is equally likely to catch any given fish in the pond? So again, it's just the total number of catfish over the total number of fish. So since we know the entire population is 1,235, and we know 541 of those are catfish, we get a probability of 0.4381, or approximately 44% chance of catching a catfish in this pond. Although the pond is now gone and the fish are relocated, so this is kind of a silly problem. Again, any questions, please email me.